Alright, in today's video we're looking at the equilibrium checkup worksheet. This one involves no algebra, so there will be ice tables, but there will be no x's, no use of the solver or anything like that. So try the questions with me as we go through it. If you've already done it, you can just check your answers, but it's a good review to pause the video and try the problems as we go. So the first one, a chemist placed 2 moles of NaOCl in a 6-liter flask and allowed that to decompose. When equilibrium was established, she found the concentration of chlorine to be 0.158 molarity. Calculate Kc at the temperature of the experiment for this balanced equation. Now when you saw moles and liters, I hope you recognized that we need to use that to find molarity. So it was placed in the flask, so those are the initial concentration numbers. So the initial concentration of the NaOCl would be moles divided by volume, so 2.00 moles divided by 6.00 liters, so that's 2 divided by 6 is 1/3, so 0.333 molarity. Now I'm going to set up an ice table here because we knew the initial information and we know something about the equilibrium information. So we're going to fill in the table including the changes. So the initial NaOCl we just calculated was 0.333 molarity. These two things were not placed in the container initially. The chlorine, it says, at equilibrium, when equilibrium was established, chlorine was 0.158, and then it says molarity. Because it says molarity, I don't have to divide that by volume, so I'll just take the chlorine concentration and put it here, which is at equilibrium, on the equilibrium line of the table. So now I have enough information to fill in the table with numbers. If we began with no chlorine and we ended with 0.158, you must have increased by 0.158. Once I see that increased, then everything on the same side of the equation does the same thing, so the NO has to increase also. Everything on the other side of the equation does the opposite, so in this case the NaOCl would decrease. Now the ratio in the balanced equation was 2 NOs for every 1 chlorine. So on the change line of your ice table, we have to pay attention to those ratios. If the chlorine increased by 0.158, I'll times that by 2, 0.158 times 2. This is how much the NO will increase by, 0.316 molarity, because of the 2-to-1 ratio. The NaOCl also has a 2-to-1 ratio with chlorine, so it's going to lose the same amount. It's going to lose 0.316 molarity. Okay? Notice the 2-to-2 ratios here, NaOCl to NO, is one way to explain why their changes are the same. So now, if the NO started with nothing and gained 0.316, then the NO at equilibrium is 0.316 molarity. The NaOCl started with 0.333, it lost 0.316, so subtracting, we end up with 0.017 molarity at equilibrium. So now we're trying to find the Kc constant at the temperature, the equilibrium constant, so we'll say Kc equals, and now I'll write the Kc expression, products over reactants, so concentration of NO squared, times the concentration of chlorine. You remember that the exponents come from the coefficients, and when there's more than one reactant or product, you multiply like that. Only gases and aqueous species are included in Kc expressions. We leave out solids and we leave out liquids because their concentrations are constant during chemical reactions. Now the NaOCl at equilibrium is 0, I'm not putting numbers in yet, so divided by the NaOCl concentration, and its concentration is going to be squared. So now we'll put our numbers in, 0.316 molarity squared times 0.158 molarity divided by 0.017 molarity squared. You can see how easy it is to make a silly little mistake. I almost made one right there. So go slowly on the test, methodically, and always be checking your sig figs. You know that I give little points for including equilibrium expressions like this, for showing your calculation of concentrations. So don't leave out those things if you're looking for full marks on a test. So 0.316, we square that, times 0.158, divided by 0.017 squared. I'm going to keep, let's see, 3 digits times 3 digits divided by 2 significant digits. I'm going to keep just 2 digits here. So when my calculator says 54.59, I'll round that off to 55 with 2 significant digits. If you said 54.6, that's probably okay, but 2 significant digits was the correct number of digits. What percentage of the NaCl decomposed in reaching equilibrium? Well, to figure that out, if you imagine you have a bunch of people in a classroom, say 20 people are in a room, and 5 people leave. Well, what percentage of the people left the room? Well, you would take the 5 people that left, and you would divide by the 20 people that you started with, and you times by 100, and say 25% left. By the same reasoning, we started with 0.333 molarity NaCl, and 0.316 molarity is what decomposed, it's what left. So to figure out the percent that decomposed, the percent of NaCl that decomposed, we'll take the 0.316 molarity, and we'll divide by the starting of molarity, 333, and we'll times by 100. Now, if we were asking what percent of the NaCl remains, or what percent is present at equilibrium, then I would focus on the 0.017 number, the equilibrium number, and divide that by the starting amount and times by 100. So 0.316 divided by 0.333 times 100 gives me 94.9%, almost 95%. Decomposed. Okay, now why did the Kc for this reaction end up being relatively large? Why did we have 55 as a Kc value here? The reason for that is because most of the NaCl decomposed. Since most of the NaCl decomposed, we can say that the reaction favors the products. It's product favored. Okay, we have very little reactants left, so it's not reactant favored. Those NaCl is becoming products, so it's product favored. And therefore, another way to say it is, we have a high percent completion. This reaction was 95% complete. So any of these things here would be a good way of saying why Kc has to be large. When a Kc value is large, you have lots of products at equilibrium and very few reactants left. So that means most of your reactants get used up. We say it favors the products. We say it's near 100% complete. This was 95% complete. Question number 2. You've got 92 grams of N2O4 in a 10-liter vessel. I already see there some annoying grams. I'm going to have to convert that to moles and then use the volume to get molarity. It was placed in the vessel and allowed to decompose. 82% remains at equilibrium. Calculate the Kc value. So again, we're going to need an ice table for this because we know the initial conditions, and then 82% remains at equilibrium will tell me something about the equilibrium conditions. So over on the side, we can convert the grams to molarity in one of 2 ways. If you prefer using formulas, we can use 2 different formulas. Moles is mass divided by molar mass. So little n, moles, is the mass, 92.0 grams, divided by the molar mass of N2O4. Once you have your moles, then you can find concentration by taking the moles and dividing by the liters, the volume in liters. So that's one way to do it. I'm going to do it with a few unit multipliers. I'll take my 92 grams, 92.0 grams of N2O4, and I'm going to convert the grams to moles of N2O4, and then I know that once I have moles, I just have to divide by the volume in liters. So I'll just put times 1 over liters, which is the same as dividing by the liters. So the first multiplier is my molar mass, so N2O4, we have 2 times 14.01 nitrogen plus 4 times 16 the oxygens, 92.02 grams per mole, so 92.02 grams is the molar mass, and the volume was 10.0 liters. So taking 92 and dividing by 92.02, hey, that's 1 mole, and divide that by 10, and we get 0.099 or 0.0100 molarity. Oops, not 0.01, 0.100 molarity. Okay, be careful rounding off. So that's the initial concentration of N2O4, 0.100 molarity. There was no NO2 placed in the container initially. Now what do I do with this 82%? Well, it's what remains at equilibrium, so this is what goes in the third line of the ICE table for N2O4. But it's a percentage, and percentages are always of something. So when we say 82%, what we mean is 82.0 divided by 100, that's what percent means, of the starting amount, so of our 0.100 molarity. That's how much remains at equilibrium. So 82% would be 0.82 times 0.1 would be 0.0820 molarity. So that's what's left at equilibrium, 0.0820 molarity. So now that we know the initial line of the table and we have a number at equilibrium, we can fill this entire table in. So I'll take 0.1, take away 0.082. The N2O4 lost 0.018. So we lost 0.018 molarity. Then on the other side of the equation, we have to do the opposite. We have to gain. And looking at the ratio 2 to 1, it's going to gain twice that number. The change line is where you have to look at the balanced equation stoichiometry. So times that by 2, and we get 0.036 molarity is the change in the NO2. And then that leaves us with 0.036 molarity at equilibrium. And now we just need to write the Kc expression and put those numbers in. So the Kc value will equal concentration of NO2 squared divided by concentration of N2O4 equals 0.036 squared divided by 0.0820. And looking at that, I'm going to keep just 2 significant digits in my answer. 0.036 squared divided by 0.082 gives me 0.016, the value of Kc. Why does it make sense that Kc for the reaction was relatively small? Kc 0.016. It makes sense that it's small because the N2O4 lost just a little bit of its initial concentration. It had a small percent reaction. 82% was left, so 18% of the N2O4 reacted. A small amount. Okay, since only a little bit of reactants got used up, we know that this was reactant favored. Okay, at equilibrium, most of your reactants are remaining. So this was reactant favored. Okay? All right. A couple more questions on the back. The equilibrium constant for this reaction is 0.015 at some given temperature. And this looks like the reverse of the Haber process. The Haber process, you remember, is the synthesis of ammonia. This is its decomposition. In a 5-liter flask at 20 degrees, The mixture has this much 0.25 molar nitrogen, 0.155 molar hydrogen, an equilibrium mixture. What is the concentration of ammonia? Now, there's a bit of a typo in the question. I shouldn't have said at a given temperature. So if in the next line I say at 20 degrees Celsius, this should have said at 20 degrees Celsius, right? So, let's see, we know two of the concentrations of gases in the equilibrium mixture, and there's only 3 gases in the equilibrium mixture. I also know Kc. So if you think about that for a minute, do we need an ice table for this? Well, there were no initial conditions mentioned at all. There's only the equilibrium conditions. So setting up the ice table for this is kind of silly. You could, but you'd have no information to put in the table except for the equilibrium line, which is fine, actually. All we need to do this question is set up the Kc expression. Kc here is equal to the nitrogen concentration times the hydrogen concentration cubed divided by the ammonia concentration squared. And looking at the equilibrium expression, we realize of the 4 things that are there, Kc and the 3 concentrations, we know all of them except 1. So we can easily just use algebra to find the one thing that we don't know. I'm looking for the concentration of the ammonia, so looking at that here and doing some algebra, just moving the NH3 out here and the Kc back down here, we get that the concentration of ammonia squared will equal the nitrogen concentration times the hydrogen concentration cubed divided by my Kc value. So now I'll plug my numbers in here. That's going to be 0.250 molarity times 0.155 molarity cubed and divided by the Kc value, which was 0.015. So grabbing a calculator, we'll take 0.25, we'll times by 0.155 to the power of 3, and then we'll divide that by 0.015. Right? That gives me 0.062, keeping 2 digits because of the Kc value there, 0.062, and that's the concentration of ammonia squared. So technically its units are molarity squared. I won't worry about that right now. The concentration of ammonia then, because this was its concentration squared, is the square root of 0.062. So that's going to equal the square root of 0.062 is 0.25, I guess, with 2 digits, 248, so 0.25, and that's a concentration, so 0.25 molarity. So that question was pretty easy. Why did it not require setting up the ice table? Because there were no initial conditions given at all, and we knew 2 of the 3 equilibrium conditions. That's why. So at the same temperature, what would Kc be for these 2 reactions? Well, we knew that Kc for the reaction up above was 0.015. What is Kc for this reaction? Well, to decide that, compare this reaction to the original, and you'll notice that what we did was we reversed the original equation. We learned in class that when you reverse an equation, what used to be products are now reactants, what used to be reactants are now products, so your Kc expression ends up getting flipped over. The math term for that is you take the reciprocal of Kc. So the new Kc value will be the reciprocal, 1 divided by the old Kc, 0.015. So 1 divided by 0.015 is 67. Notice that when the reaction in one direction has a small Kc value, the reaction in the reverse direction has to have a large Kc value because you're taking the reciprocal of the Kc. Now in the second reaction we see 6 ammonias decomposed to make 3 nitrogens and 9 hydrogens. Comparing that to the original up above, we see what we did was we multiplied the original equation by 3, okay, the original equation. And we learned in class that when you multiply an equation by a number, you're changing all of the coefficients, and those coefficients become the exponents in the Kc expression. So we learned that if you multiply by a number, Kc will be raised to the power of that number. So in this case, multiplying by 3 means the new Kc will be the old Kc, 0.015, to the power of 3. So Kc 0.015 cubed gives me 3.4 times 10 to the minus 6. 3.4 times 10 to the minus 6 is the new Kc value. So Kc values are linked to equations as balanced. If you change the equation, if you balance it in a different way or look at the reverse reaction, then you need to change your value of Kc to match that. Alright, finally we'll look at some true-false questions. So, true or false, a reaction that has reached equilibrium appears to have stopped. The key word there was appears. Does it look like it has stopped? Yes, true. That's because when you reach equilibrium, all of your concentrations, all of your colors, all of your pressures, your temperature, everything stops changing. So it stops changing means it looks like the reaction has stopped. Is the reaction stopped? Definitely not. The forward reaction and reverse reaction are always happening, but at equilibrium they're happening at the same rates, so it looks like the reaction is not changing anymore. Adding a catalyst will make Kc larger. Is that true or is that false? Well, if the reaction was not already at equilibrium, then adding the catalyst would make it reach equilibrium faster. That's true. But does it change Kc? The only thing that changes the Kc value, other than balancing an equation differently, as we did a moment ago, the only experimental thing you can do to change a Kc is to change the temperature. So adding a catalyst has no effect on the Kc value. Changing the initial conditions or concentrations changes the Kc value. Well, I just said that only temperature changes will change the Kc value, so this is false. Changing the temperature changes the Kc value. Well, as we just stressed, that's true. It's the only thing that changes Kc. When a reaction has a small Kc, its reverse reaction has a large Kc. True or false? Well, we said that just a moment ago up above. When you reverse an equation, you take the reciprocal of the Kc. So if a reaction has a small Kc, the reverse would be the reciprocal of the small Kc, and 1 divided by a small number gives me a large answer. So this is true. When you have a small Kc in one direction, the opposite direction has a large Kc. When equilibrium is reached, concentrations of reactants will equal concentrations of products. Definitely false, right? If you've done any equilibrium problems, you know the ice table at equilibrium, concentrations are rarely, if ever, going to be the same. What is the same at equilibrium is that the rate of the forward reaction will equal the rate of the reverse reaction, but the concentrations are rarely, if ever, going to be the same. A reaction with a large Kc favors the products. There'll be very little reactants left when equilibrium is reached. That's true. When Kc is large, the ratio of products divided by reactants is a large number, then that means you must have a large numerator, you must have lots of products, and a small denominator. You have very little reactants left. The reaction here is close to 100% complete. It favors the products. So large Kcs definitely produce lots of products. There's very little reactants left. Finally, doubling the coefficients in an equation causes Kc to double. Well, that's false, right? When you change the coefficients, Kc will change, yes, but doubling the coefficients will do what to the Kc value? Remember, we learned that if you multiply by a number, Kc will be raised to the power of that number. So instead of doubling, the Kc would be squared in this case. So this is a false statement. All right, I hope that helps. This is like the first half of the equilibrium problem solving. The second half involves algebra. The second half also involves the reaction quotient. Be sure you're familiar with both types of problems, these easier ones as well as the more difficult algebra problems. There are videos I posted online with the more difficult examples also. So good luck.